Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Jason Haffner, who is Professor of Physics and Astronomy at Rice University. His lab at Rice studies nanophotonics and interfacial biology. Welcome, Jason.
Thanks. Thank you very much.
Yeah, thanks for doing this. So before we get into your papers, I want to set the context of these two things. So nanophotonics and interfacial biology, what do those things mean?
Yeah, sure. So nanophotonics is just sort of a part of nanoscience in general. You know, nano has been a big thing since sort of the 90s. This idea that if we shrink material or matter or control materials down to the nanometer scale, they interact with the world differently. And that's sort of big picture what we study. So as you can imagine, nanophotonics is doing that with light. So normally we think of light as not being real nano. You know, the wavelength of light is about 500 nanometers. This is why we have like a limit to what we can see in an optical microscope. But as the light interacts with materials down at the nanometer scale, some materials will focus the light down to the nanometer scale, or heat up due to the light in special ways. So really, big picture, nanophotonics is just how can we manipulate light at the nanometer scale with nanomaterials.
Yep. Okay, we'll get into the details of that. Does it have any sort of computational applications also?
Does it have? You say computational?
Yeah. Does it have some sort of chip design or anything like that with that? Or
right? Yeah. Okay. So sort of two ways to go with that. Yeah. So computational, so we use many computational tools, and it's actually pretty critical. Many areas of research these days, but especially these interactions. In terms of an application, there are ideas. There are some aspects of why light would be better than electrons on chips. It's still definitely sort of a research phase stage thing. How do you do the couplings and in my field we can send light, we can turn light into an electronic excitation and send it down a metal wire and have it come out the other end as light, which is really cool, but it's very lossy. Metals, you lose a lot of the energy. So it's definitely being looked at, but for now, I don't think in terms of completely taking over a chip, that's still quite a ways away.
Yeah, I was just thinking, one of the issues is obviously this quantum tunneling issues that conventional chips get into.
Yeah.
This issue of heat on chips. So I was just wondering if there's a direction there. What is interfacial biology?
So really there is just a general way to talk about membranes. So if you think about, the picture of a cell that you saw whenever the last time you took biology was, it had this outer circle of the membrane and then inside all these organelles. And that picture kind of sells membrane short because really the membrane surrounds every one of those organelles. The cell is full of membranes, and on these interfacial membranes, lots of the biological action happens. So membranes are a huge part of sort of microbiology and cell biology, but they're also the hardest to study, which we can get into later when we talk about what we're doing with it. So really, to me, it just means, you know, where the liquid meets another liquid, or the liquid meets the solid, if you want to think of the membrane as a solid. That's the interfacial part.
And so does it have some applications in, so you mentioned cell biology. So COVID getting into the cell and using the cell infrastructure to replicate itself, do we have some applications in that direction?
Yes, for sure. So that's getting sort of into synthetic biology, you know, hijack. That's getting into all biotechnology, really. Sort of, I've sort of worked on sensors a lot, and it's always an interesting realization to me that the most powerful sensing technologies we have are from hijacking biology. You know, assays, we work great, and the critical part is the antibodies we get from an animal. And you know, PCR, the famous thing, you know, amplifies DNA. It's completely hijacked biology. So so I forgot what I was talking about, but but yeah, so synthetic biology is that idea, taking that even further. Membranes are just one component of all that, I would say. You know, they need to understand membranes to make a lot of that work, but a lot of biology you can hijack without really understanding exactly what's going on. So even if we don't perfectly understand membranes, they'll still be a component of that kind of technology. There is one area that is membrane, you know, biomembrane specific, and that is you take the cell's membrane and you lay it flat on a surface and then integrate it into sort of a chip kind of a technology. It has to be kind of a wet chip. So these are called supported lipid membranes. And the idea is you can take some of the ion channels and things from a cell and then turn them into sensors on a chip. And that also is kind of like the photonics, the nanophotonics thing. It's in progress. It's not happening any day now, but it's definitely an interesting idea that's coming along.
Yeah. And so I want to start with one of your older papers. It's entitled "A Tunable Plasmon Resonance in Gold Nanobelts."
Right.
I don't know anything about this, Jason. So gold nanobelts, I'm just assuming, you know, this is some sort of a gold nanotube of sorts.
Right.
What exactly is a belt?
Yeah, so the belt really is just sort of the way that we say it has a rectangular cross section. So, you know, generally it's just a wire. It's something that's really long in one dimension and then nano in cross section. But for some reason, you know, the names of these nanomaterials are all just kind of made up by the people that write the papers. And sometimes they're comical, you know, like for a while there was an obsession with food, like all new nanomaterials were named nano and then after a food. But belts usually mean just something with a rectangular cross section. So that's why we stuck with the belt in the name.
And plasmon resonance, what exactly is that?
Yeah, so plasmons are sort of a subfield of nanophotonics. So there's different ways you can manipulate light at the nanometer scale. You can go with dielectric structures like glass, or you can go with semiconductors, or you can go with metals. So metals do this interesting thing. So if you think, you know, the reason a metal is a metal is it has those free electrons in it that, you know, drift around and make currents. So when light hits a metal, you know, light is an electric field that oscillates, so it pushes those free electrons. And that's why metal has the optical properties it has, and there's lots of details there. But what's interesting is if you have a very small particle of a metal and the light comes in, it pushes the electrons up and down, and that's sort of like a mass on a spring. You know, when the electrons go out of the metal, they want to get pulled back in because they leave positive core, you know, ions behind them. And if they go down the other way, they want to get pulled back in. So the electron's like a mass on a spring. Light is like a driving force. So you can think of a plasmon resonance as just like a mechanical resonance of a mass on a spring. So at a certain light frequency, the electrons move up and down really big and cause a lot of scattering and a lot of absorption. And that's basically a plasmon resonance. And it's sort of, it doesn't happen in all metals at the visible wavelengths. So some metals, it'll happen in the IR, some of it happen in the UV, or it's a problem that the metals oxidize. Like most metals, if you make a teeny nanoparticle, the whole thing would oxidize. So there's a few metals like gold and silver that have this resonance in the visible, and they're inert enough that you can actually have a piece of metal that's 10 nanometers and not a piece of oxide. Yeah.
Yeah, you know, I sometimes feel, Jason, that these properties that these precious metals have, like gold and silver, it's almost like somebody designed this to be that way.
Yeah, it's really, I mean, the history of this is unbelievable. It goes, you know, prehistoric, they would find that the sand from certain rivers, when they made stained glass, it would be red. And the reason is it had little chunks of gold in it. And then Michael Faraday is the one that figured out that's actually, it's the metal, it's the gold that's doing it. And if you take gold and get it into small enough particles, it turns red. So Faraday figured that out. And then Mie scattering theory was one of the main things he was figuring out is why do these gold particles turn red? So one of the original electromagnetic theories of scattering was based on this as well. So it's sort of been experimentally seen for a long time, but it's only been used since around the 2000s when we started to get enough nanochemistry going to make really monodisperse shapes of different kinds of gold and silver nanoparticles. So that's when the field really exploded with all these different shapes and silly names and everything, coming out. Yeah.
And so if I understand this correctly, Jason, so you have a rectangular cross-section nano belt of gold. And in the visible wavelength, when light hits that, there is some phenomenon like the electrons, free electrons moving out and then pulled back in. They sort of, you can get into some sort of a resonance there.
Right.
So that's the idea, right? So can we use this for anything from a practical perspective?
Yeah, so that's really what I found interesting about this area. And I actually don't remember exactly why we did the first paper, but retrospectively, what I find interesting, I don't remember what I was doing at the time, is that, there's huge studies on these plasmonic nanoparticles and many others, quantum dots and everything, for like what I'd call zero-dimensional particles. So even if it's a little elongated rod or it's a cube or whatever it is, it's still nano in every dimension. It's like a point particle to us. And there's a lot less on just elongated things like wires. I mean, people in the field will say, wait a minute. I mean, there are semiconductor nanowires. Those are very widely studied. But metal nanowires, which you would think would be the most fundamental material in nanoscience, for some reason just aren't as frequently synthesized and aren't as widely studied. There are applications and people are, pursuing them. So one is transparent conductors. So if you want, maybe for a sensor or something, you want something that completely see-through, but will conduct electricity, like maybe you need to pass current through it, or maybe you don't want it to get static charge on it, whatever. One way to do that, well, there's a lot of ways. One is to use sort of some semiconductor that's transparent and visible, but still enough current will flow through it, like indium tin oxide or something. Another would be to put a really thin metal film on it, but a really thin metal film still absorbs some light, so you still get a little bit of a tint, like if you think about sort of the IR blocking windows and buildings, they always look a little bit green, But another idea is to coat it with really fine, metal wires that you could just spin on from solution. And then their optical absorption would be just negligible. But because they make a network, they would give you a little bit of conduction, which is all you need for a lot of these applications. Or their net sense, would be dense enough that if you touched it, you would definitely complete a circuit that could potentially be a sensor.
Yeah, so this resonance phenomenon, can it be used in any sort of information storage?
Yeah, so that's another thing that was interesting about these wires is there had been a little bit of synthesis on them before. We were kind of following another paper, and it was when I looked at them in a microscope that we saw the colors. Like nobody had really thought about whether they would have a sharp plasmon or not. I mean, a sharp resonance that would give it a color. And we look at them in the right kind of microscope that we used a lot, and they were all red and green and yellow. And we realized they have this sharp resonance. So that gets into sort of a lot of potential applications of these plasmons, some in information storage. So, you could shine, like we actually have some of the belts that change color from one end to the other. So you could shine maybe red and excite one end red and see if green comes out the other end, or excite the red end green. So there's lots of, these are sort of futuristic ideas, but they're mostly conduits. But then there's a lot of things you can do where you can, when you send light into one end of the wire and turn it into a plasmonic excitation, and then it comes out the other end as light again, while it's at plasmonic excitation, it's really shrunk down to a very sort of novel state of light. And people have worked on, if you put a quantum dot nearby, when it goes by, it can excite the quantum dot. And if it excites the quantum dot, then you lose the plasmonic excitation. If the quantum dot's already excited, it'll just go by. So there's a lot of interest in putting sort of quantum dots near these wires to make sort of single photon kind of transistors. So a lot of work has gone into that. The belts, we showed that they acted as conduits, but we didn't, we're not really a quantum, we're not that kind of a group. So we didn't go much further. Yeah.
So what exactly is a quantum dot?
Yeah, so quantum dot, so that is another kind of nanomaterial. So that's a really, really small piece of semiconductor. So it sort of acts like just a big atom or molecule, because you get these discrete states. And then when you shrink the semiconductor down to really small size, the spacing between those states gets so big that the spacing between the states gives you like visible photons. So when you see like a quantum dot LED TV or whatever, and I think they make quantum dot TVs now, those are just quantum dots that their size determines their color. And that's how it emits the light.
Yeah. So I was going to say a lot of applications in display,
right?
I would imagine.
Yeah.
Right.
For the semiconductors, because they're not so lossy, the metals that are acting like wires in between them, like that I worked on or that I'm synthesizing, it's the high loss in the metal that's an issue. So there's lots of tricks people work on, like what kind of an electronic mode do you use to transmit this light? If you have one where the field is in the metal, you get a lot of loss. But you can try to find another mode where the field is mostly outside the metal, and then you get less loss. So that can be done at a macroscopic scale, but similar tricks are being tried sort of at a microscopic scale. Yeah.
The energy is really small, right? It cannot have any storage type application.
Yeah, so I think, so you'd have to get into statics, and making capacitors would be the generic way to store. I mean, there are ring modes in dielectric structures where, a photon will just go in there and ring around for a long time. And they're so low loss, it lasts a while. But I don't think anybody's thought of it as an energy storage yet. I think compared to any chemical system, it doesn't even come close. So I think that's why they're still using the chemistry.
Yeah, I was wondering more, sort of space applications where the weight, to storage ratios are, sort of very critical. I wondered.
There. So if we get away from the photonics a bit, and then these really fine wires could be electrodes in sort of ultracapacitors is another application. You want to get the highest, you want to get, if rather than storing your energy chemically in a battery, you're going to store it, I'm making air quotes, electrostatically in a capacitor. You just want the biggest surface area you can get. So there's always interest in increasing surface areas of structures by just sort of coating them with very fine wires like this. And that's one application. Now that we're doing the nanobelts again, we're kind of thinking about,
Yeah. Long time ago, I remember, Jason, when electric cars were beginning to, make sense, there were thoughts about using capacitors as energy source rather than the batteries that we currently have. I don't know what happened to that. Is that still in play?
I think, fields come and go. So I know ultracapacitor is kind of what I was talking about just a second ago about putting the nanowires on there. Ultracapacitors did get very popular, especially as nanomaterials started coming out. And I think they're still working on it. I mean, I think it's ultimately just a capacity issue. It's just they store less energy, but they can deliver it much faster, and they weigh less. Right. But they store less energy. So ultimately, if they don't store enough to drive all the way to San Antonio from where I am, then it's not going to be as good as a battery. But I think the ultracapacitors do have sort of niche applications where you need that power really fast without, melting a battery down. So I think they have niche applications, but I think replacing big capacity batteries, I don't think they're there yet. So.
Yeah, it's sort of correlated with the infrastructure. So if I have a charging station, let's say every 50 miles reliably, and it takes me only 5 to 15 seconds to charge up, it will be almost like driving through.
So if you had infinite infrastructure capabilities, you wouldn't have to stop, right? Just have some electrodes on the ground and charge, then you're basically a train eventually,
Right. Yeah, I want to go into another paper. It's related, obviously. Novel plasmonic structures based on gold nanobelts. So it's a little later than in the first paper. So what is what are you looking at here? You talked about quantum dots already. Was that the sort of the direction?
So the novel structures. We just found all these novel structures, so we wrote a paper about them. One, though, was the fact that, so this gets a little bit more into the plasmonics resonances of those belts. So if the cross section of the belt is square, the plasmon resonance is green. It happens at green wavelengths or green frequencies, 530, whatever, nanometers. And then if it goes elongated, it happens more in the red. So, 700 nanometers or so. And we found there are structures where it would just evenly shift from green to red. So structurally, the belt is going from a square cross-section, then it's spreading out into a wide cross-section. But then optically, when you look at it, it's just this nice little thing that changes color. So in a sense, we thought this is kind of like a spectrometer, but a very different kind of spectrometer. So in a normal spectrometer, you take light of all these mixed colors and you shine it off of like something called a diffraction grating, and that makes it reflect out at different angles. But this little plasmonic, I think we called it a plasmometer. I don't know if we said that in the paper, but what we could do is say you wanted to measure how different plasmon wavelengths enhance like quantum dot emission. If you make your plasmon energy match your quantum dot energy, then you get more light out. So I think one figure in that paper was we took one of these tapered belts, we called them, and covered it with quantum dots and just looked at the emission, and it was brightest where the quantum dots were resonant with the belt, somewhere between red and green. So it was basically like a structural way to measure the excitation spectrum of the quantum dots. So that was just sort of a weird thing nobody, never really thought about being able to do, but it's something that this weird structure let us do.
Yeah. So potentially some applications in astronomy then, right?
Yeah. So let's, if you wanted to sort of, if you wanted to, really the idea is it would miniaturize something. Like if you needed, I mean, long term, maybe we could make it higher resolution and everything, but it wouldn't require like the long arm of, hitting a grating. And then when you hit a grating, you got to let the light spread out for a very long distance. So this is sort of like a spectrometer you could put on a chip because you don't need that separation. It's just a completely different kind of way to do it. You don't need the angle difference from the grating is very small. So you got to let it go for a long way to get the wavelength separated, where this is more of a direct separation.
So again, applications where weight is a consideration, maybe telescopes, space telescopes.
Yeah, potentially. Yeah, if you sort of had these on something where you could detect which part of the belt was getting excited, then potentially you could really shrink this and have sort of a chip level spectrometer. So I could imagine that.
Yeah. I want to go into one of your recent papers, Jason, structural analysis by enhanced Raman scattering. So Raman scattering, what exactly is
Raman
that?
scattering, it's a special kind of light scattering. So if you think about when light scatters off of an object, then let me start over because it depends on the color of the object. Okay, so let's imagine we have a white object, right? And you have a white marble, and if you shine green light off of this white marble, you're going to get green light scattering off of it. Because the marble being white just tells you that it scatters all wavelengths the same. So that's called Rayleigh scattering. Yeah. So this color that goes in is the same color that comes out. So if you think about it in terms of photons, there was no energy change. The energy of the photon coming in is the same as the energy of the photon coming out. But now if you replace this ideal white marble with a molecule, the molecule is vibrating. So molecular vibrations are an important thing in analysis and chemistry, and that really happen. So when the light scatters off the molecule, it can actually lose some energy to the vibrations. Like the light can create a vibration, or since the molecule is already vibrating, it can give some energy to the light. It can take energy away from the vibrations. So most of the light has the same color, but a little bit of light gets its color changed by interacting with the vibrations. So if you take a spectrum of the light that scatters off something, most of it will be the original color. You use a laser, so it's monochromatic. But then a little bit in the wings of the spectrum will reflect the vibration of the molecule. So this effect was discovered by Sir Raman in I think the 20s or something like that. And he won the Nobel Prize and everything. So it was a very fundamental idea that light does lose energy when it bounces off something. But now it's a huge tool for analysis. So in chemical analysis, vibrational analysis is very powerful. And it's usually called IR, because the energies of the vibrations are at infrared wavelengths. and kind of way infrared, not just kind of a little bit infrared. I can feel it, but way out there. And unfortunately, that's just the technology for that isn't as good. You know, the sensors aren't as sensitive. You can't make lasers. It's not as bright, etc. So Raman scattering is sort of an interesting thing. It's a way to use visible light where our technology is very good. You know, we have lasers and single photon sensors and everything, but you get the vibrational information because you just get it based on how much the visible light shifts. You're not directly trying to measure the infrared vibrations. So basically, Raman is just a way to get this sort of fingerprint spectral information with visible technology.
So can we get sort of a structural information, meaning you know, a complex molecule or something like that, and get information?
Yeah, so that's the power of Raman. So it's called a fingerprint spectrum because it has the, you know, if you imagine every one of these big complicated biomolecules or other big molecules all vibrate in their own special way. So you can say, well, this vibration is going to tell me exactly what molecule I have. So that's sort of an ideal situation. As you can imagine, with millions of different molecules, a lot of them vibrate pretty similar, you know, so you don't really have this, you know, perfect, I can identify any molecule in the universe based on its Raman spectrum. There's a lot of overlap, but there's still plenty of chance for insight. So especially in research labs, if you're working with very pure solutions of identical molecules, you can learn quite a bit from the Raman spectrum. Yeah. And on like these biomembranes I talked about, if you can make a biomembrane from a single lipid component, lipids are the molecules that make membranes, then yeah, there's a lot of structural information you can get, and you combine the Raman with other methods and you get a lot of insight. But if you just shot a Raman spectrometer at a tree, you know, you're just going to get a big mess jumble of spectra, and it's harder to apply in sort of the natural world.
Yeah, I was just thinking, Jason, so I wondered if there's some sort of diagnostic applications, for example, in pharmaceuticals or something like that, where, you know, once the product is approved, you know precisely, you know, what that chemical is supposed to be. And, you know, if you want to look at if there is any sort of contamination or something like that, would it be sensitive enough?
Yeah, so so you sort of hit exactly where Raman is used. So widely used in research labs. Industry is harder, but basically just think of industries where they're looking at pure things, and that's where it's probably going to be used. And I'm not like an expert on the world uses of Raman, but pharmaceuticals is definitely one, right? They make all these pills. They want to make sure there's nothing they don't expect in the pills, so they could scan those under a Raman spectrometer.
Right.
Cosmetics also, you don't want to put something on your skin that you don't know what's in it, and those tend to have a fairly finite number of ingredients in them. So yeah, so there are some real world applications. Raman is not super sensitive, but you know, for those applications, I mean, optics is so good now that it's kind of good enough. And the key is, you know, you could use it in those applications because you have a giant milligram scale pill to look at. If you want to detect like one molecule in the pill, then Raman, that's the problem with Raman, is it's not super sensitive. So, yeah.
Yeah, you talk about here, the lipid double bond was found to be oriented normal to the bilayer with 13 angstrom from so you can really potentially get the real structural information of a complex molecule, right? If you know precisely what that molecule is. Yeah,
but this gets into the so there's Raman and now there's SERS. So this is now getting into what brings in the nano component. So let me explain real quick. SERS is surface enhanced Raman scattering. So what happens is, so the Raman I described was just a plain wave of light, hits a material, scatters off, and that's all you're looking at. So, and as I said, Raman's not real sensitive. So, you know, if you send in 1 million photons, 999,999 are going to Rayleigh scatter, and 1 is going to Raman scatter. So you don't get a lot of signal. But these metal nanostructures, you know, that have these Plasmon resonances, they basically focus the light down onto a molecule at their surface, and then they act like an antenna and broadcast the scattering. So that's what the surface enhanced part means. Molecules at their surface get greatly enhanced Raman scattering. And the enhancement can be sort of like 100 million, just because of the physics of how it works. So you get really huge enhancements. So SERS, surface enhanced Raman scattering, has actually been shown to give you the vibrational spectrum all the way down to a single molecule. If you make the right arrangements of metal structures, you can get just huge enhancements, and watch single molecules jump around and everything. So that, you would think that would have big applications. It's just hard to get SARES, it's hard to make it real reproducible. So what we did is say, forget getting the super high enhancements. Let's just look at particles in solution and take medium enhancements and see if we can understand the signals and get structure. That's basically what we did in that paper.
Yeah, it's really fascinating. You say here that the new method can determine specific interfacial structure under ambient conditions with microscopic quantities of material and without molecular labels. So, yeah, I see, just like you're doing it in the lab, potentially industrial applications. I see more on the diagnostic side, Jason, because it takes little energy, it's easy to, I'm just making statements, I don't know if this is true, to convert that into some sort of an instrument.
That's what we're working on, well, long term. So it is true the method is very easy. So, and if I was, right now, this is how science works. You get a way to do something. Then if you really want it to catch on, you got to convince other people to do it, or you want to look at their samples or I'm sort of in that stage of, I've now demonstrated this. Now I got to look at a bunch of systems and get people excited and realize what this method can do. So it's sort of like, I kind of think of it a little bit like NMR. NMR is a widely used method, and it's a method that really is a spectroscopy, but there's a little bit of structural information buried in the spectra. So that's basically what I'm doing with SARES. It's just spectroscopy, but we can tease structural information out and sensing and things like that. But it's a lot easier. Really, if somebody already has a Raman spectrometer, like all of industry does, you really just need the nanoparticles and all the computational stuff I had to do, on DF, calculating molecular properties and everything. So it's something that could be very easily uptaken by industry or other researchers, relative to like NMR, where you've got to install a whole facility. But finding what to do with it, that's trickier. So I think one thing I've thought about is this SARES has the same problem with Raman, that there's just too many signals. But if you put this lipid bilayer like we're putting on the particles, then that sort of holds back most things. Like the only thing that's going to get near the particle is stuff that likes to be on a lipid bilayer. So you sort of got this instant screen for, 99% of the junk in the solution, and it will just accept sort of the membrane attracted molecules.
Yeah, I mean, if you have a practical instrument, presumably, Jason, you can, attach a brain to it. You can do some machine learning techniques. If the decision is sort of binary, meaning it is good stuff or it's not good stuff.
No, that's
it might be.
Yeah, that specific bond you mentioned, that carbon-carbon double bond, that's actually used in it's diagnostic for like cancer. When they're doing the margins when they're in surgery. So there's one group at UT Austin who is actually doing sort of during the surgery mass spec. Mass spec is a very powerful industry, so everything can be solved by mass spec. And they have this little tool that they'll do surgery and they'll like suck the margins around the surgery and get a quick measurement on how much carbon-carbon double bond is in the lipids. And that'll help guide them in whether that's malignant or they need to cut further. So this is another thing that in principle, we could begin to kind of measure the relative amount of carbon double bond in the tail relative to the normal lipids. So yeah, and then that would be something where you'd want a machine making that decision quickly rather than me sitting there going, well, I don't know. So.
Yeah, and if you can do it right in the operating theater, right during the procedure, oftentimes, what happens is you go back and you study it and you say there is enough margin, so you have a second surgery. So if you can avoid that.
Yeah, no, this group actually, the method was so successful, they actually have a mass spec in the operating room, at least in this test demonstration phase. So it's a little wand that just sucks material, goes straight to a mass spec. Because mass spec is very advanced technologically. But I guarantee if they can put a mass spec in an operating room, I can put a little baby Raman spectrometer. That's another advantage of the Raman. It's just a little teeny. It's not it doesn't have to be a big fancy instrument. So it's pretty low tech compared to other things. So,
right. Yeah. I mean, that's the attraction here, I think. The instrument will be really small. It can be potentially incorporated into existing hardware. presumably. And if it's giving you information during a procedure that, things are working or not.
Yeah, there's lots of examples of people trying to use Raman in these ways during surgeries on natural samples. And that's really a direction the field, I think, is headed. And what I'm working on some now, even in my own work on the method where we're looking at the lipids is, we use quantum chemistry to predict these modes. Part of this method I did was we used quantum chemistry programs you got to know something about how the molecule vibrates and how the Raman properties change. And I did that. I'm not a theorist, but there are commercial packages that let you do that. But I did that on just an ideal molecule structure, and that'll predict one spectrum. But then molecules are always fluctuating around, around all the single bonds, their rotations. And how does that affect the Raman spectrum? So my latest paper, I didn't send it to you, it's still under review, is looking at how molecular conformers affect these spectra and affect the interpretation of the Raman spectrum, which is just a further complication in this interpretation. Yeah. But really, that's key to all the applications. Is I've read papers, and I don't want to be critical, but I've read papers where they say, here's a spectrum, and this is the funniest thing about vibrational spectroscopy, is they always say, we assigned the modes. And I think in this field, I think assign is a euphemism, which basically means we don't know that these are the modes, but these are the assignments of the modes. Because it's just, you get a lot of dense information, but I think knowing what every peak really is, I think there's a long way to go to really know.
Yeah. And as you say, human bias get into interpretation. So you're going to get a lot of confirmation bias.
Yeah, and this is where really quantum chemistry needs to just get faster and faster. So, and it is getting faster and faster. So, just the ability to calculate a Raman spectrum on a big molecule only came out like 20 years ago. And I'm sure only one, you needed a supercomputer to do it. And all the calculations I'm doing now in 2021 are on a gaming PC. I just spent about an $1,800 gaming PC, and I can get pretty accurate calculations on pretty big molecules. But it needs to go even further, and we need to basically combine, molecular dynamics to get all the conformers and these quantum calculations for every step of the molecular dynamics, right? That's called ab initio molecular dynamics, and that is not fast yet. But eventually it will be, and I think we could calculate really highly realistic Raman spectra at that point.
Yeah, a lot of interesting things here, Jason. So in conclusion, you have done a lot of work in this area of nanomaterials. If you look forward 5 to 10 years, where do you think we will be? I'm thinking more in terms of applications. I know that you are sort of sitting at the intersection of research coming out of the labs. There appears to be at least some practical directions. Do you see we will get there in 5 years?
I think this is always the tough question. I think a lot of the nanomedicine that was sort of talked about in the early 2000s, a lot of it is getting very real. And I think one reason people don't realize why is that as we know with cancer at this point, there's not going to be a day that we cure cancer, right? There's not going to be a single method that cures all cancers. But a lot of these methods are really happening in the clinic. The one from my field that I think about is the photothermal therapies, where they put sort of the gold nanoparticles, gold nanoshells. A lot of this actually came out of Rice from my colleague Naomi Hollis and Jennifer West. And they put those and they go to a tumor, and then you shine the infrared light and it heats up and cooks the tumor, inside the body. So that was first shown around 2000. And you say, well, where is it? Why, and then they had to go to human trials. It takes forever, but it really is happening in people, and it's really being used. It's just, they're going to be used according to the doctors in the cases where they should be used, which isn't going to be all the cases. So I think all this nanomedicine, all these applications are basically going to sneak up, and one day we're going to say, oh, well, it's everywhere, because there are real patients doing it now. And I think the doctors just have to figure out, when is it better than the standards, and when should we try one over the other. But I think the nanomedicine is going to really become more and more common.
Yeah, it's the approval process, the standard of care definition. It has to get into the medical school education. So there's a lot of process friction.
I know that, and I'm not even one of the PIs trying to do it. I mean, you could talk to my Hollis and West. I'm sure they're very well aware of all the difficulties. But after 20 years, I mean, people really are being injected with these. And I'm just speaking of that one specific application because I know it. I'm sure there's many nanomedicine applications that really are starting to happen. Yeah.
Yeah. It's exciting. Yeah, this has been great.
Sure, it was
Jason.
great.
Thanks
It's
so
great to
much
talk
for
to you.
spending time with me.
Oh, thanks.
Yeah, and good luck with this research.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.